Hi, girls. How are you? I'm back here with you once again today, and today's lesson is a really short one, and its title is Phase Difference. But before we know about phase difference, you need to know about the term phase. So, phase is actually a physical quantity that describes exactly the position and the direction of motion of a particle. So, it's usually applied to particles that are vibrating, which means the particle or object is either going up and down or it's going back and forth. Okay, and the easiest way to show the phase of an object is by drawing a phasor, and hence the word phase, phasor, they're all kind of related. So I have over here a simple harmonic motion particle, let's say, which can move up and down, and this red dot points to a moment in time when it's on its way up and over here. So the phasor that represents the phase of this particle is this blue arrow pointing that way, tells you where it is. Now, if on the other hand, instead of moving upwards, it was in the same position but moving downwards, then you cannot have the same phasor. Then the phasor would look like this over here. Okay, it's on the other side. So this quadrant is for moving upwards above equilibrium. This quadrant is moving downwards but still above equilibrium. Anything above the horizontal axis represents motion above equilibrium. Anything below here represents motion below equilibrium. And so I have one over here. There's a particle here moving downwards, and so that's a phase that represents that. If on the other hand it was below equilibrium but moving upwards, then your arrow would be in that quadrant. Okay, so that's to do with phase. And now the next thing is about phase difference. The moment you hear the word difference, it implies there's more than one particle or one object. So phase difference has to do with two objects that are in simple harmonic motion. So I don't have two springs or two pendulums here with me because we're all doing remote learning. So I'm just going to use my hands. So if you had two simple harmonic motion particles that are going up and down, they have the same period and the same amplitude, and they both peak at the same time, they go through equilibrium at the same time in the same direction, and at the bottom we say they are vibrating in phase, or their phase difference is zero. Okay, but if on the other hand one particle was up and the other was moving down, and they're crossing each other in opposite directions as they're going through equilibrium, then we say they are in opposite phase, or their phase difference is 180 degrees. So phase difference can be expressed as an angle, or it can be expressed as time. And phase difference can also again be represented by phasors. Now the thing to remember is if both the simple harmonic motion particles have the same period and the same frequency, they will always have a constant phase difference. Okay, now the amplitude doesn't matter, okay, because a period is unaffected by amplitude. So I have here a diagram. So there are two circles just to represent their two objects in simple harmonic motion that's out of phase, and they've both got two different amplitudes. So just showing the phase, one of them, the red one's at equilibrium, the blue one, which has got a higher amplitude, is at a different position. This angle between these two vectors, the phasors, is their phase difference as an angle. Okay, and in order to express phase difference correctly and to have more meaning, we need to say which one's leading and which one's lagging. The word lead means which one's ahead, and lag is which one's trailing behind. Okay, and in order to be able to use the word lead and lag correctly, we just need to remember that phasors go anti-clockwise. So in this diagram, the blue one is actually, because they're both going anti-clockwise, so the blue one's leading the red one, or the red lags the blue. Okay, now here's another diagram to show phase difference. I've got the graph as well as the diagram. So I've just got them both the same amplitude. They are actually moving, but at a particular point in time, A is at equilibrium, B is at the end position, And so if you draw a graph for A as it goes around, it's going to be a sine curve. If you draw a graph for B as it goes around, it's peaked, so it's going to be a cos curve. So because they're going anti-clockwise, we always say B leads A, or A lags B by 90 degrees. So we've got the angle as well. Okay, it's also possible to use this as time, but for that we need to know period. So, and in the calculations, when you're solving the problems, you'll see how you can express phase as time as well. So I hope that made some sense to you, and I hope you have a good rest of the day, and take care of yourselves, and bye for now.